Okay, so for our final video for simple harmonic oscillations, we're going to look at the pendulum. Okay, so you have a pretty good idea of what a pendulum is. You put a mass on the end of say, a string, and you just let it swing back and forth. Now, a few things we have to pay attention to. The first is that the string we attach it to is massless. Okay, and that the only mass concentrated in the system is just in whatever bob we put at the end of that rope. Okay, so this thing's going to swing back and forth, and so the argument here is that a pendulum is a simple harmonic oscillator. Okay, and as it turns out, it's only true if the amplitude of the swing is small. Okay, and when we measure the amplitude of a swinging pendulum, we're really looking at the angle that it makes with the vertical support. Okay, so on the picture, we're just going to draw the two angles equal on both sides because, like amplitude, they're equal on both sides. Now, realistically, we know that a pendulum will die out and eventually come to equilibrium, but in the perfect scenario, it would swing out to these amplitudes on both sides each time. Now, remember, in order for an oscillator to be a simple harmonic oscillator, it needs to follow this relationship from Newton's second law. So let's go ahead and work through that and see if we get a similar relationship. Okay, so if we focus on where this mass is now, okay, out at an angle theta from its support, okay, the only force acting on it is gravity. All right, so that means what's going to cause this thing to rotate is a force that's perpendicular to that string. Okay, so what that essentially means is that the component of gravity that is perpendicular to this radial line would be, if we look at that little triangle, is simply gravity times the sine of that angular displacement. Okay, and so since that is a perpendicular component, okay, recall that that perpendicular force is going to cause a torque on that mass and causes it to rotate, or rather swing, through that angular displacement. Okay? And don't forget, to cause a torque, not only do you need a perpendicular force, but you also need a distance from the pivot. And in this case, since we hung the mass from a string, the pivot, or the string, it is a certain length from the pivot, and that represents our level arm for the torque. Okay, so from the mass at the end of a string of length L, gravity causes a torque to cause it to swing. So now that we know that it's causing rotation, we can use Newton's second law in rotational form. Okay, so you'll remember that to calculate, or to rather look at torque through Newton's laws, it simply states that the net torque is equal to the moment of inertia times the angular acceleration. Now, torque, remember, is radius times the force. So in this case, the radial arm was the length L, and the force was mg sine of the angle. Now it's negative because remember that that torque is trying to restore the mass back to equilibrium. So that's why the negative sign's there, is because this is a restoring force. For the moment of inertia, recall that that's the sum of the mass times how far it is from the rotational point squared. So in this case, it's just the mass of that bob times the length of the string squared. And then angular acceleration is actually the second derivative of angular position. So hopefully none of that's really new. Now if we go through and do some algebra steps here, first we see that the masses will cancel. Okay, and then one of the L's will also cancel. Okay, and so we're left with this expression, that negative g over L sine theta is equal to the second derivative of angular position. Now, remember we said that at small angles, a pendulum is a simple harmonic oscillator. And the reason we said that is because if the angle is small, and by small we mean it is much less than 10 degrees, and you could try this in your calculator, the sine of that angle will equal approximately what the angle is. So if you do the sine of like 9 degrees, it'll come out to right around an answer of 9. So we can make that substitution then. We can replace the sine of theta with just theta. Now, when we do that, look at this expression. This is an expression of a simple harmonic oscillator, where the second derivative of the position is equal to the negative of the square angular frequency times the position. That's exactly what we have here, where the angular frequency is the square root of gravity divided by the length of the string. Okay, that also means that we can then find the period of a pendulum, which would be 2 pi divided by the angular frequency, or times the square root of the reciprocal, which would be L over G. But notice here, the important concept is there's no mass in this equation. So that means that the mass of the pendulum does not affect the period of its swing. The only thing that affects it is how long the string is and what the gravitational field strength is. So you remember on your quiz, we had a question about if I moved an oscillator to another planet. And on the quiz, it wouldn't change the period because a mass on a spring only matters about how much mass and how much spring force. But if you're swinging a pendulum and I move it to another planet, that will affect the period because it depends on the planet's gravitational field. Okay, so another example of a pendulum is a physical pendulum. Now, what we just did is prove simple harmonic motion for a simple pendulum. Okay, and what makes the pendulum simple is the string, or the thing attaching the mass to the pivot, is massless. So in a physical pendulum, that basically means any object you pick up and you allow it to swing from a certain fixed point, that is a physical pendulum. So if you just imagine an object here and it's not even fixed at its end, this object will swing, okay, and it turns into a pendulum. But since it has a physical distribution of mass, we can't use the same equations. We got to rethink this. So the first thing to think about is that gravity is acting on the center of mass, and that's the only force causing a rotation. Now, the same argument holds. Okay, if we draw out the triangle here, you see that the only component of gravity that's going to cause any rotation is the sine component. So just like before, the sine component of gravity causes a torque, but instead of it causing it on the mass, it's causing it on the center of mass. Okay, and then because it's a torque, we got to know the distance, and if you look at it, it's a distance, we'll just call it x, from the pivot point. So however far the center of mass is from the pivot point, that's our radial arm when we're calculating the torque. All right, so Newton's second law in rotation, net torque is equal to moment of inertia times angular acceleration. The torque is Rf, so R is the distance x, F is the sine component of gravity. Now the moment of inertia could vary, depends on the type of object, so we're just going to keep it I for now. And angular acceleration is the second derivative of position. So if we simply divide the moment of inertia to both sides, okay, and we do the same thing with the small angle approximation, okay, we get the expression minus mgx over the moment of inertia times theta is equal to the second derivative of the angular position. Again, this is simple harmonic, where in this case the angular frequency would be the square root of mgx over moment of inertia, and the period is 2 pi times the square root of that reciprocal. Okay, so this is a question that's routinely asked on the AP exam, but it's a formula you do not have on your formula sheet. And that's primarily because they want you to be able to show how to get that period. Okay, so study that process because it's the same nearly every single time. The only thing that could change in your calculations is the moment of inertia, because that's just dependent on the type of object. Okay, so the final type of pendulum we're going to talk about is something called a torsional pendulum. And a torsional pendulum is something like you hang a piece of string and then you put an object at the end of the string, and rather than swinging it, imagine twisting it up. And then when you let it go, it starts to rotate around that central string. But as it twists more and more, the tension gets tighter and tighter until it starts to twist the other way. And then it twists past equilibrium, tightens up in tension again, and then recovers the other way. So in order to do this problem, you have to know what the torque is, and typically the torque depends on how much radians it's twisted up through. So you'll usually just see this as some general equation. So in this case, it's usually a constant, just we'll call it B, times the angle that it's rotated through. Okay, and that constant B could be any number of complicated mathematical determinations. For your purpose, just know that it's a constant, and we're talking about how much this whole disk has rotated in terms of an angle. So we're going to go ahead and solve it in the way we've done everything else. We're going to look at torques. So the net torque is what we just gave as the function, minus b times the angle. Then you got moment of inertia times the second derivative of angular position. So if we divide the I, we get again a simple harmonic oscillator, where the angular frequency is the root of b over I, which means the period is 2 pi times the square root of the reciprocal, I over b. Okay, now a torsional pendulum actually popped up on a free response exam back in 2011. So, and then every once in a while there's a multiple choice question on one. So you just have to know that setting it up is the exact same way as doing all other pendulum questions. The physical pendulum is set up the same way as doing a simple pendulum. Okay, so just practice setting those equations up multiple times so you kind of get the pattern. And then if you're asked that question, well, you know the process in doing it.